Welcome to the fascinating world of wave optics. Unlike ray optics, which treats light as straight lines, wave optics explores the wave nature of light. This approach helps us understand phenomena like interference, diffraction, and polarization. In this video, we'll dive deep into how light behaves as a wave, setting the stage for understanding interference patterns and their significance in science and technology. Let's begin by exploring what makes wave optics so unique and why it's essential for explaining effects that ray optics simply cannot. To truly grasp wave optics, we must first accept that light behaves as a wave. This means it exhibits properties like wavelength, frequency, and amplitude, just like water waves or sound waves. The wave theory of light was first proposed by Christian Huygens, who suggested that every point on a wavefront acts as a source of secondary wavelets. This concept is crucial for understanding how light waves interact with each other, leading to the beautiful and sometimes surprising patterns we observe in experiments. Huygens' principle is a cornerstone of wave optics. It states that every point on a wavefront can be considered a source of tiny secondary wavelets which spread out in all directions. The new position of the wavefront is found by drawing a surface tangent to these wavelets. This principle helps explain how waves bend around obstacles and through openings, setting the foundation for understanding interference and diffraction. It's a simple yet powerful idea that revolutionized our understanding of light. One of the most important concepts in wave optics is the superposition principle. This principle states that when two or more waves overlap at a point, the resulting displacement is the sum of the individual displacements. In the context of light, this means that when two light waves meet, they can add up to create brighter regions or cancel each other out to form dark regions. This is the basis for interference, which we'll explore in detail next. Interference is a phenomenon that occurs when two or more light waves overlap and combine. Depending on how the waves align, they can reinforce each other, creating bright fringes or cancel each other out, resulting in dark fringes. This effect is a direct consequence of the wave nature of light and is not explained by ray optics. Interference patterns are not just beautiful, they're also incredibly useful in scientific measurements and technology. There are two main types of interference: constructive and destructive. Constructive interference happens when the crests of two waves align, making the resulting wave larger and brighter. Destructive interference occurs when a crest meets a trough, causing the waves to cancel each other out and produce darkness. These two types of interference are responsible for the alternating bright and dark bands seen in many wave optics experiments. One of the most famous demonstrations of interference is Young's double-slit experiment. In this experiment, light passes through two closely spaced slits and forms a pattern of bright and dark fringes on a screen. This pattern is clear evidence that light behaves as a wave, since only waves can produce such interference effects. The experiment not only confirmed the wave theory of light, but also paved the way for modern physics. Perform the double-slit experiment. A coherent light source, such as a laser, is directed at two narrow parallel slits. The light passing through the slits acts as two new sources of waves, which then overlap and interfere on a screen placed behind the slits. The resulting pattern of alternating bright and dark bands is a direct result of constructive and destructive interference. Bright and dark bands seen in the double-slit experiment are called interference fringes. Bright fringes occur where the waves from both slits arrive in phase and reinforce each other. Dark fringes form where the waves arrive out of phase and cancel each other out. The spacing and intensity of these fringes depend on the wavelength of the light and the distance between the slits. Positions of the bright and dark fringes in an interference pattern can be predicted mathematically. The condition for constructive interference bright fringes is that the path difference between the two waves is an integer multiple of the wavelength. For destructive interference dark fringes, the path difference is a half-integer multiple of the wavelength. These simple equations allow scientists to design experiments and interpret results with precision. For clear and stable interference patterns, the light sources must be coherent. Coherence means that the waves maintain a constant phase relationship with each other. Lasers are excellent sources of coherent light, which is why they're often used in interference experiments. Incoherent sources like ordinary bulbs produce random phase relationships, making interference patterns blurry or invisible. Interference patterns are most distinct when monochromatic light is used. Monochromatic means the light has a single wavelength or color. Using light of different wavelengths can cause overlapping patterns, making the fringes less sharp. This is why lasers which emit nearly monochromatic light are ideal for interference experiments. The concept of path difference is central to understanding interference. Path difference refers to the difference in distance traveled by two waves from their sources to a given point. If the path difference is a whole number multiple of the wavelength, constructive interference occurs. If it's a half-integer multiple, destructive interference results. This simple idea explains the regular spacing of bright and dark fringes. Distance between adjacent bright or dark fringes is called fringe spacing. Fringe spacing depends on the wavelength of the light, the distance between the slits, and the distance from the slits to the screen. By adjusting these parameters, scientists can control the appearance of the interference pattern, making it a powerful tool for precise measurements. Interference isn't just a laboratory curiosity, it has real-world applications. For example, interference is used in antireflective coatings on glasses and camera lenses, in interferometers for precise measurements, and even in fiber optic communications. Understanding interference allows engineers and scientists to design better optical devices and technologies. In-film interference is a common phenomenon seen in soap bubbles and oil slicks. When light reflects off the top and bottom surfaces of a thin film, the two reflected waves can interfere, creating colorful patterns. The colors depend on the thickness of the film and the wavelength of the light. This effect is a beautiful demonstration of wave optics in everyday life. Newton's rings are another striking example of interference. When a convex lens is placed on a flat glass surface, a series of concentric bright and dark rings appear. These rings are caused by the varying thickness of the air film between the lens and the glass. Newton's rings are used to measure the flatness of surfaces and the quality of lenses. Michelson Interferometer is a powerful instrument that uses interference to make extremely precise measurements of distance and wavelength. It splits a beam of light into two paths, reflects them back, and then recombines them to produce an interference pattern. Changes in the pattern can reveal tiny differences in path length, making the Michelson Interferometer essential in scientific research. Interference isn't limited to the lab, it's all around us in nature. The brilliant colors of peacock feathers, butterfly wings, and even some minerals are due to interference of light reflected from microscopic structures. These natural examples show how wave optics explains the vibrant patterns and colors we see in the world. While interference is about the combination of waves from different sources, diffraction refers to the bending and spreading of waves when they encounter obstacles or openings. Both are wave phenomena and they often occur together. Understanding the difference helps us analyze complex patterns in wave optics experiments. When light passes through a single narrow slit, it spreads out and forms a diffraction pattern on a screen. This pattern consists of a central bright fringe and several dimmer fringes on either side. The width of the central fringe depends on the wavelength of the light and the width of the slit. Single-slit diffraction is another clear demonstration of the wave nature of light. When light passes through more than two slits, the resulting interference pattern becomes even more complex and sharp. Devices like diffraction gratings use this principle to separate light into its component colors, making them invaluable in spectroscopy and analytical chemistry. A diffraction grating is an optical device with many closely spaced slits. When light passes through, it creates a series of sharp, evenly spaced interference fringes. Diffraction gratings are used in spectrometers to analyze the spectrum of light, helping scientists identify materials and study atomic structure. Polarization is another property of light waves that can affect interference. When light is polarized, its waves vibrate in a single plane. Polarized light can be used to control and analyze interference patterns, and it's essential in many optical technologies, including LCD screens and polarized sunglasses. Fiber optic cables use the principles of wave optics, including interference, to transmit information over long distances. By carefully controlling the phase and coherence of light signals, fiber optics achieve high-speed, low-loss communication. This technology forms the backbone of modern internet and telecommunications. Interference filters are optical devices that use thin film interference to selectively transmit or block certain wavelengths of light. These filters are used in cameras, scientific instruments, and even in environmental monitoring to isolate specific colors or signals. We encounter interference effects in many everyday situations. The colorful patterns on a CD or DVD, the iridescence of a soap bubble, and even the rainbow sheen on oil spills are all caused by interference of light waves. These familiar sights are vivid reminders of the wave nature of light. Interference patterns provide a precise way to measure the wavelength of light. By analyzing the spacing of fringes in experiments like the double-slit or using interferometers, scientists can determine wavelengths with incredible accuracy. This capability is essential in fields like spectroscopy and optical engineering. The sensitivity of interference patterns to tiny changes in path length makes them ideal for precision measurements. Interferometers can detect movements as small as a fraction of a wavelength, which is useful in applications ranging from astronomy to engineering and even earthquake detection. While interference is a powerful tool, it does have limitations. Interference patterns can be disrupted by vibrations, temperature changes, or incoherent light sources. Careful experimental design and environmental control are necessary to obtain reliable results in sensitive measurements. The study of interference and wave optics has had a profound impact on science and technology. It challenged the particle theory of light and led to the development of quantum mechanics. The insights gained from wave optics continue to influence modern physics and engineering. Modern physics shows that light exhibits both wave and particle properties, a concept known as wave-particle duality. Interference experiments, especially with single photons, reveal the mysterious and fascinating nature of quantum mechanics, where probabilities and superpositions rule. Interference principles are at the heart of many modern technologies. From the design of lasers and optical sensors to the development of holography and advanced imaging systems, understanding interference allows engineers to create innovative solutions for communication, medicine, and industry. Holography is a technique that records and reconstructs the full three-dimensional information of an object using interference patterns. By capturing both the amplitude and phase of light waves, holography creates stunningly realistic images that appear to float in space. Lasers are ideal sources for interference experiments because they produce highly coherent and monochromatic light. Laser interference is used in applications ranging from precision measurement to medical imaging and even in entertainment, such as laser light shows. Modern communication systems, including fiber optics and wireless networks, rely on interference principles to transmit and process information efficiently. By manipulating the phase and coherence of signals, engineers can increase data rates and reduce errors, making communication faster and more reliable. Artists have long been inspired by the vibrant colors and patterns created by interference. From iridescent paints to holographic art, the interplay of light waves adds a dynamic and captivating element to visual creations, blending science and art in beautiful ways. Wave optics continues to be a vibrant field of research, with new discoveries and applications emerging all the time. From quantum computing to advanced medical imaging, the principles of interference and wave behavior are opening up exciting possibilities for the future. Let's recap what we've learned. Wave optics explains the behavior of light as a wave, leading to phenomena like interference and diffraction. Interference patterns arise from the superposition of waves, and their analysis has led to major advances in science and technology. Understanding these concepts is essential for anyone interested in physics or engineering. If you want to see interference in action, try simple experiments at home or in the classroom. Shine a laser pointer through two closely spaced slits or observe the colors in a soap bubble. These hands-on activities make the abstract concepts of wave optics tangible and memorable. When performing optics experiments, especially with lasers, safety is paramount. Always use appropriate eye protection and follow safety guidelines to prevent accidents. Responsible experimentation ensures that learning about wave optics is both fun and safe. Wave optics is a core topic in physics education. Understanding interference and related phenomena helps students develop critical thinking and problem-solving skills. It also lays the groundwork for more advanced studies in physics, engineering, and technology. To reinforce your understanding, consider questions like, what is interference? How does the double-slit experiment demonstrate wave behavior? What are some real-world applications of interference? Reflecting on these questions helps solidify the key ideas of wave optics. If you're interested in learning more, there are many excellent books and online resources on wave optics and interference. Exploring these materials will deepen your appreciation for the beauty and complexity of light as a wave. Wave optics and interference reveal the hidden patterns and possibilities within light. From the colors in a soap bubble to the precision of modern technology, these principles shape our understanding of the world. Thank you for joining this journey into the wonders of wave optics. Keep exploring, and let the light guide your curiosity.